Okay, hello and welcome to my channel. Today we're going to talk about the effective potential. So to begin, let's first take a look at what we have derived in the last video. Our Schrödinger equation for central potential, d squared dr squared. U is a function of r squared 2m squared. Let's write it like this. Plus v of ru of r. Okay, so take a look at this Schrödinger equation. We can see that there is this term here that is new, and you can recognize that this term is the angular momentum, and angular momentum has is in the angular space, so you can put it in you can group it with the potential essentially. So that is where you get your effective potential. So your V effective is going to equal to V of R plus your L squared over 2mr squared. So this is your effective potential, and it would look something like this when you put it on a graph. This guy is the central potential, so the sinkhole, like that, and the angular momentum term would be something up here, like this. Okay, so your effective potential would be something between these two. That is going to be something like this. There we go. That would be your effective potential. So this is V effective. Right, so that would be your V effective. And now we're going to find out about the bound of it. To do that, you take a look at the origin, and according to the effective potential, it has to your U have to vanish at the origin. Okay, so we're going to take our wave function as U r over r instead for the RE of r, and YLM of the angle theta and phi. So now we're going to try and normalize this guy. So the normalization, the cube x of your wave function, well, d cube x is gonna be the r squared dr, the solid angle. Okay, so sub it here. That would be from 0 to infinite for the radial part, r squared u r squared dr. Next is our YLM. This part, well, by orthonormality equal to delta, so this term is inevitably equal to 1. Okay, so you have this term is 1 already, right? So this term, the r gonna cancel out, so what you're left with is the integral from 0 to infinite of u squared dr has to be equal to 1 for this to be normalized. Okay, so back to our Schrödinger equation. We want to see its behavior at the origin. So we take r to go to 0. Okay, take r and let that go to 0. What you get is that your Schrödinger equation, r squared plus 1 u equal to, would have to go to 0 as well, so it's going to be around 0. So from here you can cancel these two terms and move the minus over here, move that over there, so get your d square u dr square equal to l plus 1 over r square u. Right, so now you got this thing, and we're taking it the limit of it, so this would be an Euler-Cauchy equation. And I won't be solving this, but your solution would be either u equal to rl plus 1 or u equal to r minus l. Okay, so these are your two options. And right off the bat, you can say that your r to the l minus l is not valid because, well, when you take the re value of this, say r1 of r and r2 of r, so this one is rl plus 1 over r. This is r minus 1 minus l over r. This is rl. This, on the other hand, is 1 over r 1 over rl plus 1. And you can see when you take r to equal to 0, this term equal to 0. So as these guys goes to 0, r1, r2, r1 goes to 0. But on the other hand, r2 goes to infinity. Therefore, it would spike up as a delta function at the origin, so that is not acceptable because it is a potential, so it has to be 0 in the origin, right? Okay, so that is pretty brief since this part is not very long but very important. Remember to take the rl plus 1 instead of the r minus l. So this guy cross it away. It cannot be our solution. Okay, so that's it for today. Goodbye.